What are the odds? What are the odds? What are the odds?
So I think the study of probability is very important as a business analytics practitioner because it really is one of the underpinnings of a lot of the tools that you end up using on a day-to-day basis. So Unit 1 is all about exploring what does it mean when we talk about a probability and where can we use that in not only our real life, but then also in business analytics. So what I'd like to start out with is just a couple examples of where we've seen the words probability or chances, as I like calling it, just in everyday life and where it crops up in business analytics. And I think we're all pretty familiar with listening to the weather forecast and hearing about some weather occurring with a particular chance. So the weatherman might say, hey, there's going to be a 70% chance of at least 2 inches of snow overnight. And if you were like me as a kid, you loved hearing those forecasts because you had your fingers crossed hoping it was going to be a snow day. And so what did it actually mean for there to be a 70% chance of that occurring? It kind of felt like it was more likely than not that maybe school was going to be delayed or canceled because that snow was going to happen. But what does it mean from a mathematical and utilitarian point of view when we talk about the probability of some event? And tying it into business analytics, well, if you worked for the analytics firm, say at Comcast, or for any sort of cable TV company, well, you might know that they're in a world of hurt. A lot of people are essentially cutting the cord, canceling their cable contracts because they can just watch TV online at this point. And so when a customer fails to renew a contract, we say the customer has churned, and that's something that analytics teams study really quite often. And so the analytics team might go to the boss and report back and say, hey, there's a 1 in 4 chance that this particular customer, which by the way, this customer is called support 3 or more times, that type of customer has a 1 in 4 or 25% chance of churning, essentially failing to renew their contract. So what does that 25% really mean? What is that 1 in 4 chance really trying to get at? And this might be a familiar sight to a lot of us, kind of just emerging from COVID and all of the grocery stores running out of products. You see a lot of empty shelves here. Supply chain analytics is a big field of business analytics, and inventory control policy tries to be designed so that you minimize the chance or the probability of a stock out. So here we see a lot of products missing from their shelves. Whatever the control policy is that's dictating how much is being shipped and restocked clearly isn't doing that great of a job. And so analytics can help us try to quantify, well, just how often, what's the percentage chance, what's the probability that this particular policy will yield to a stock out of a product. Then we might say, I just had soup for lunch this afternoon, that this particular brand of soup is in fairly high demand. There's a 35% chance that there's going to be a stock out at some point over the course of the week. So what does that really mean? That's what we want to get at. Now, one thing I've done really quite often at UT is worked with the development office. Their main focus is on getting more alumni to donate back to the University of Tennessee and in larger amounts. And we've studied what characteristics and traits are associated with a high probability of donating, a large amount donating. And so that's where probability comes up in their study. So the development office might claim that the probability that an alumnus will donate, say, $20,000 or more over the course of his or her lifetime, be a major donor, that probability is 3%. So what does that really mean? If we go and track down 100 of those alumni, exactly 3 will have made these large donations over the lifetime. That's really the main question that we want to answer here. What do we mean when we say that the probability of an event is X? 10%, 20%, or kind of equivalently, what do we mean when we say the chance of something happening is 1 in Y? Maybe 1 in 4, 1 in 10, etc. So that's the question that we would like to answer here. Now, It might surprise you, but it's somewhat controversial what we actually mean by the word probability. We haven't really agreed on what the probability of an event really is. And there's two main camps, and because we're business analytics practitioners, we're going to take a very particular viewpoint called the frequentist viewpoint of probability, the frequentist definition. And this makes sense because in business analytics, most often we're concerned with how often various events occur. So if we're in supply chain analytics, we want to make sure that soup is on the grocery store shelves, we're worried about how often a stockout is going to occur. So how often will a stockout occur if inventory is reset? Say at 20 at the start of a week, we'd like to know how often, kind of in the long run, we expect a stockout to occur here. Or if you are, say, designing ads and you're trying to maximize the click-through rate, one thing you might want to know is, well, how often is someone going to click on an ad with a particular design? The frequency of some event of interest. If you're driving for Uber trying to pick up a few spare bucks, you are thinking in terms of frequency. How often are we going to get a request for a pickup, say, from Market Square? Is that a good place to kind of park your car and wait for a call to come in? And if we're working for Kroger, their analytics team, we're studying what types of items that people tend to purchase together, we might like to know, well, how often does someone buy dry pasta and also tomato sauce? It's going to be pasta night at their house. So in business analytics, I think it makes the most sense to think about probability along this line, how often a particular event occurs. And so we're going to start out by coming up with a fairly informal, but what I think fairly useful definition of probability. We'll get into the nitty-gritty details as we move along into the discussion. And so I'm going to lay down what I like to think of as the frequentist view of probability. So we're interested in whether some event does occur. If it doesn't occur, we want to know how often it occurs. And so this boxed sentence here really captures what I think is what we mean in business analytics when we talk about probability. So rather informally, the frequentist view of probability is kind of taking that probability to be the long run fraction of time or proportion of time that some event of interest occur. So if we're studying stockout probabilities, we might say, well, the probability is 20%. In the long run, about 20% of weeks end up with a stockout. We're thinking in terms of frequency, how often an event happens. Now, it takes a little bit of getting used to figure out what this long run fraction of time is really referring to, because it's a bit of an abstract concept. I haven't written down anything concrete, like after 1 million different times the event had the chance of occurring, a billion. What does this long run fraction of time really refer to? And I think it's useful to just think in terms of this, in terms of just exploring it. Let's write a probabilistic simulation just to see, well, what happens as we check to see if some event has occurred after more and more and more time has gone by. And so we'll stick with an example that we're all really quite familiar with, just flipping a fair coin. In this case, there's only two options, either a heads or a tails here. And so we all know that the probability that the coin would come up heads is going to be 50%. So I can say without really knowing too much about probability that in the long run, the fraction of coin flips that end up heads is going to be 50%. That kind of makes sense to us. But let's investigate a little bit further. Let's run a probabilistic simulation just to see what this, in the long run fraction of time, what that's really trying to get at. So let me switch over to RStudio very quickly. And on your summer exam, you had a little bit of practice with the sample command. And the sample command is able to draw outcomes at random, like heads versus tails. So I'm going to actually open up a brand new R script here. And what I'm going to do is I'm going to run the sample command with the first argument being the vector 0, 1. So I'm going to pick at random between these two outcomes. And I'm going to pick 11 of those outcomes, with replacement, because I might have more than, say, a single 1, which I'll use to represent heads. 0 will represent tails. And so if I run this line of code, this would provide me an example sequence of heads and tails. 0 is tails, 1 is heads, over the course of 11 flips. And so the frequentist view of probability is taking the probability of some event as the long run fraction of time where we see that event occur, And so, out of curiosity, let's go ahead and calculate what that fraction is as we flip the coin more and more. What is the fraction of heads that we've seen after a certain number of trials? And so, because each time I run the sample command, I'm going to get a slightly different sequence of coin flips, I'm going to go ahead and left arrow that into just a vector named flips. That'll go into the environment. We can print out to the screen what is stored in that vector. And so we see we started out with tails, tails, heads, heads, etc. So I'm going to use a command that I like called the cumulative sum, which when applied to a vector essentially gives us a running count, a running sum of the elements in that vector. So if I were to look at, say, the fifth element of the cumulative sum of flips, which is right here, I see a 2. That means if I were to add up all of the elements up to and including the fifth element, that sum would equal 2 here. We see that, yep, that's the case. If I sum up 3 zeros, 2 ones, I get a 2 here. So if I take the cumulative sum of the flips and divide by the integer sequence, 1, 2, 3, all the way up to 11, that's my shortcut here, that's going to be in the fraction of coin flips that have come up heads so far. So these first 2 coin flips, well, they were both tails, so 0 is the percentage of heads that I've observed so far. But as I add in more and more flips to the experiment, what I see is that this fraction is kind of bobbing up and down. I know that the probability is 50%, but the observed fraction is sometimes a little bit below, sometimes it's a little bit above. And so that's what this slide is actually trying to get at. It's trying to show us visually, well, what does that fraction look like as I sit down and flip this coin more and more. I've drawn a red line here at 50%. What we know, kind of instinctually, is the probability of that event occurring. And this fraction is slowly evolving over time, essentially more and more coin flips. And so when we sit down and talk about the frequentist view of probability as being the long run fraction of time where an event occurs, long run is obviously going to be more than 11 here. So let's actually investigate, well, what's going to happen if we were to add in more and more coin flips, more and more trials to this simulation here. So if we were to do that, well, what we see is that the trajectory of this fraction looks like it's kind of veering a little bit closer and closer to 50% as we add in more and more flips. It starts out fairly far away, but it gets a little bit closer. Now, in this particular sequence, we're kind of drifting a little bit farther and farther away from 50%. And even after 100 coin flips, we don't see that this fraction is that close to 50% here. But 100 must not be really in the long run. That's an abstract concept anyway. Let's try to investigate a little bit further for what the long run might actually be. So let's take this even further and look at 100 million coin flips and what the fraction of those coin flips so far over that sequence have come up heads. And here's really what that long run fraction of time is trying to get at. We know the probability of getting a head is 50%. And so if we look at the fraction of heads after 100, 10,000, 1 million, 100 million, this is all on a logarithmic scale right here, what we see is that trajectory is slowly inching towards that 50% number. And in fact, after 100 million flips here, we really can't tell the difference between what the actual fraction of coin flips that came up heads was and that 50%. It looks like it's smack dab right on top of that red line. And so that's what we really mean by in the long run. It's not after a particular number of coin flips or a particular number of trials here. It just means after a whole lot of them. And in fact, by the end of the course, you're going to be able to come up with a tool, technique, that actually says, well, after 500 trials, here's how far off I think the true probability of some event is based on a simulation I've run or based on an experiment that I've run as well. Now, let me also go back to RStudio here just to point out something important with the lecture notes that you'll see throughout the semester. So all of these graphics, all of the code that you've seen in previous slides is going to be available in a companion file to each of the PDFs for the lecture notes. So the name of that file is going to be the same as the name of the PDF. So in this case, 1Z, probability definition rules. And you're going to look for a file with the extension .r. And so what that does is it automatically scrapes out all of the code that I used when I was writing these lecture notes and provides it in a nice, easy file. So if you ever need to find some of the code that's been covered in the lecture notes here, you want to see how some of these plots maybe were created. Well, what I've done is I've tried to name that code after the name of the slide that you see in the lecture notes. So if you wanted to reproduce this plot right here, well, this is called Extended Investigation 2. You could do a Control F and find, or just scroll down a little bit. So here's the code that actually goes into making that plot. And in this case, it requires a little bit of code before it. Sometimes the code stands independently of the other chunks. Other times you might need to run a few more chunks before it. But let me actually just run that code just because, well, this evolution that we saw as that trajectory inched closer and closer to 50%. Obviously, that's going to depend somewhat on, well, what was the actual sequence that was observed. If I were to rerun this experiment, different sequence, what is that trajectory going to do? Is it still going to settle down right at 50%? Well, that's some of the use of looking at this code here. So going back to investigation 1, you'll notice I have a set seed command to prime the random number generator at a particular point for reproducibility. And then what it does is it samples zeros and ones, heads and tails, each with a probability of 50% for a total of 100 million flips. So I'm actually going to run that. It takes a while, obviously, flipping a coin 100 billion times, even for a computer, isn't that fast. And I'm going to run the rest of the code. This is actually going to produce what was in the extended investigation 1, going out to 100 coin flips. And you can kind of see that that's going to be the case because in the plot, I plot a vector called selected and y, and selected is just the integer sequence 1 through 100. So that's what I got. Now what I do is I go and pick and choose a smaller subset of flips to look at. So not all 100 million, but kind of along equal increments here. And so here's our plot. So what I can do if I wanted to remake this, but maybe with a different sequence, I could leave off that set seed. If I were to go and run this code again, highlight that chunk, and then run it, it would regenerate that sequence of 100 million coin flips without setting up the random number generator to be in a specific spot. And here we go. We see that that fraction is really quite far off after, say, 10, 100, maybe even 1,000 flips. But in the long run, leaving that a little bit open, but meaning after a lot, after 100 million coin flips in this case, once again, we're settling essentially right at that 50%. And just for illustration, running that one more time, we'll see a very similar behavior. A lot of variation to what the observed fraction of coin flips that came up heads for a small number of flips, but in the long run, it kind of settles down onto that number. And so that's what we mean by the probability of some event when we talk about probability in business analytics. Informally, we're studying how often an event occurs. We're studying the frequency of events. So we're going to take the frequentist view of probability. The probability of some event is just the long-run fraction of time where that event occurs. All right, so if we were to zoom in on that last plot, where we saw it was basically at 50% after 100 million coin flips, if we zoomed in even closer to 50%, notice the y-axis here goes from 50% in the middle up to 50.1%, down to 49.9%. It still hasn't landed exactly on 50%. It doesn't stay there forever. It's just kind of teetering a little bit above, a little bit below, but ever kind of reaching closer and closer and closer to that 50%. And that's what we mean by probability. It's a little bit unsatisfactory because it never really quite gets there and stays there. It just gets closer and closer and closer and closer. The difference between that probability and the fraction you've measured gets closer and closer to zero as the number of trials increases. Now I'm going to throw a little wrench into this discussion, a little bit of something for you to think about, because this is a bit bizarre the first time you're introduced to this, and it doesn't quite make much sense, and it won't be probably for a few weeks until we can fully wrap around this phenomenon that I'm about to introduce here. So what we saw by running that simulation, we ran it 3 times, was after 100 million coin flips, there was basically no difference whatsoever between 50%, the true probability, and the fraction of coin flips that came up heads. We couldn't tell the difference. But what if I look at this from a slightly different angle? What if instead I looked at the actual number of heads that came up after n flips, let's say? And we know that if the probability of coming up heads is 50%, we would say that, well, after n flips, we would expect about half of them, n over 2 flips, to be heads. Now, here's kind of the crazy thing. What this plot shows us is the difference between just n over 2, the expected number of heads, and the actual number of heads that we've observed as the simulation progresses. And here's the crazy thing. As we add in more and more flips to our simulation, more and more trials, what we see is that the difference between the expected number of heads, just the number of trials over 2, and the actual number of heads starts growing and growing and growing. And so here's two things that you're going to want to keep in your head when we think about just probability in general. Probability means something very specific, especially in business analytics. Probability is all about the long-run fraction of time where your event occurs, the proportion of trials where you see your event occur. When we do talk about probability, it's not going to be a comment about how many times we've seen an event occur in the absolute sense. So when we talk about probability, it's in terms of the fraction of trials we've observed. It's not about the actual number of times that we've seen that event. The actual number of times we have seen our event of interest actually starts to grow more and actually farther away on average from its expected value, much like what we see here. Now, that doesn't really make sense at this point. We're going to have to really study why that's true mathematically to be fully convinced of it. But that's the one thing I want to leave you with right now, is that when we talk about probability, it's a frequency of how often we see those events. What fraction of the time do we see that event occur? It's not a comment about how many times we see that event occur in the absolute sense. So if you go to Vegas and you're going to bet some money on roulette and you see all the last numbers have been red, and you know that red and black are equally as likely, just because we've seen a lot of reds doesn't mean that the blacks are going to start actually catching up to that. Yes, the fraction of spins that come up red or black is going to be equal values here, but that doesn't necessarily mean the actual number of reds versus blacks we see are going to cancel out in the long run. Kind of a weird little quirk about probability. We'll get to the bottom of that mystery by the end of the course here. So this slide kind of summarizes what we just discussed here, kind of one of the big things we learned from that simulation. It's all about proportions. It's not about the number of flips that come up heads. So sadly, we're kind of stuck with this definition, this frequentist definition in terms of business analytics, as we are interested in seeing how often events occur. And at this point, you might be a little bit underwhelmed as to the discussion, because I left it kind of vague and open-ended. It's the long-run fraction of trials where we see some event occur. But I didn't tell you what long-run really meant. You know, is that 100? Is it 1,000? 100 million, like what we saw in the simulation? What do I mean by that? And unfortunately, we can't really do any better. In the long run is really just kind of an abstract concept. And technically it's after infinity trials, but no one's going to conduct that. And so we're going to have to be left with that little bit of ambiguity. The nice thing is that we're going to actually be able to talk about how close the observed fraction of trials where we saw an event occurred, how close that is to the true probability. We'll be able to talk about how far off we are at a later point. But for now, I'm going to kind of leave you hanging, unfortunately. That's as good as we can get. There's only very few cases, and we'll talk about those in this unit, where we can actually calculate the probability of some event exactly. Otherwise, if it's some really too difficult to calculate mathematically sort of an event, we can never really truly know the numerical value of a probability. And that's kind of sad from an epistemological sense. If you've studied philosophy and kind of limits on knowledge, what we can and what we can't know, this is kind of a downer. You know, in science, we like to get to the truth. And what we see is that if we're going to talk about probabilities, we're never really going to know it, except for a very few cases here. So from a philosophical standpoint, I'm leaving you hanging here. We're never really going to know the true value of some probability. But the upshot is, especially in business analytics, we don't actually really care what that number is. As long as we've closely estimated it, we're going to be happy. You know, does it really matter if it's a 20% stock out probability versus 20.02%? That's basically the same number. Very often in business analytics, we just got to get in the ballpark, and that's going to be good enough for us.
What are the odds?